Okay, hello everybody. So especially those who survived this first section. So today I will speak about another aspect, okay, of higher derivative quantum gravity. That is, I will show how we go from ultraviolet to infrared. Okay, because last lecture we saw that if we want to have renormalizable quantum gravity, then we need higher derivatives. And higher derivatives produce ghosts, and ghosts means potential instability and loss of physical unitarity and unitarity of the S matrix in particular. But we saw how in principle it can be solved. But today we shall deal with more simple problem. Okay, that how quantum gravity looks from the infrared perspective. Okay, so the transition between ultraviolet and infrared. And in the last lecture, I will discuss how we try to make calculations in the infrared. Okay, without worrying about ultraviolet. So the main notion on the way from ultraviolet to infrared in quantum theory is decoupling. And so decoupling of massive modes in quantum gravity. So I will discuss first of all what means decoupling, or at the classical level it's something very simple. Then I will show you how we can calculate the non-local form factors from Feynman diagrams. Everything what I will tell is basically you can find in some textbooks, but maybe not exactly in this form. And then we discuss the difference between ultraviolet and low energy limits. So everything, all this part certainly corresponds to the so-called momentum subtraction scheme of randomization. So we know that there is a minimal subtraction scheme which was introduced by Hopf in the 70s, which is the simplest one. So, but it does not give you information about this part about decoupling. So then you need what people call physical randomization scheme. And the version which I will deal today is momentum subtraction scheme. So there are other possibilities. And then I will go to more complicated issue, which is more related to gravity, and discuss the decoupling in the toy model with force derivative. And finally, I will discuss some more subtle issue, which is actually not published yet. So I will show you what we can expect, because the decoupling in higher derivative quantum gravity was never calculated in full. So it's an open question up to some extent. But I will show you what we can expect if we make calculations. Okay? So, based on general theories. So, first of all, what are the references? The classical reference about decoupling theory is Appelquist and Carson, 75. They found this decoupling, formulated this decoupling theory for QED. It is very famous paper. Actually, if you take textbooks like Berestetsky, Lipschitz, Vitaevsky from 60s, okay, it's elder. I think it's in some form it is there. You can find it. And actually, if you look to these more advanced subjects like Sudakov, amplitudes and things like that, people knew much more than this. But in 60s already. But this Appelquist and Carson, they formulated this decoupling theorem at quantum level in a very clear way. Now, decoupling is a part of the general situation, general, let's say, approach, which is called effective approach. I will discuss this in the last lecture in the afternoon. And the standard reference here is this review paper by Manahar. This is also lectures, but all but. And this was published in some book, but everybody uses this one. There are many others. There are like books and especially book by Donahue, Goldstein, and standard model and others. But this is, I would say, this is the best review. It's not very complicated and clear. Now, pedagogical introduction to what I will show you today is the main part, technical part, how you calculate form factors. You can find here in this book, the textbook. Okay, there are also exercises and things like that. And in curved space-time, the first calculation was done in this paper by Eduard Gorber. He is now in Kiev. He is, how to say, correspondence member of Ukrainian Academy of Science. But at that time, he was our visitor in Shapiro. And we wrote with him these 3 papers about decoupling in curved space. After that, there were many other papers of this kind, including by us and by other people. So then you can calculate it by diagrams. I will show you full details. And then there is this famous paper of Barvinsky-Lukowski, who found how to make the same calculation using the heat kernel solution. And technically, the difference is huge because here the first calculation required 190 pages and like 4 or 5 months. And with this heat kernel solution by Avramidin, Barvinsky-Lukowski, it takes like a couple of hours. So the difference is very big. So if you want to technically make this calculation, it's better to, and won't save time. So it's better to use heat kernel solution because it's ready. Finally, this is the last paper with our student. Now he is postdoc, Wagner, and he made a big calculation also in the mixed sector of higher derivative theory. Okay, let's go. So first of all, what is the decoupling at the classical level? It's something very simple. Imagine you are in the infrared. So you have the classical Euclidean propagator of some massive field. So how you present this propagator in the infrared? So the leading term is 1/m², and then you have this series. Now what you can observe here is that the particle as itself disappears because we identify the particle as the zero of the denominator in the pseudo-Euclidean region, right? So mass of the particle is the position of the pole. And here there is no pole, you only have 1/m². Okay? In pseudo-Euclidean, this would mean that k² never approaches m². Okay? Because energy dominates over the momentum. Okay, very good. So the question is, what happens in this kind of propagator? How you can have something of this sort if you go to the loop corrections? This is not real question because in loop corrections, this is example of loops in the semi-classical gravity. When you have external line of gravitons or gravitational perturbations and loop of massive field. This is exactly what I discussed yesterday. This type of diagrams. So you see, this integral does not go for small momenta. The integral over momenta goes from 0 to infinity. So you might think that this feature that if you have a low energy and the propagation disappears should not manifest in these diagrams. But on the other hand, as physicists, we know that physical sense of this diagram, this one is less important, okay, in some sense. Physical sense of this diagram is the following. You have a graviton, then it creates particle and antiparticles, then they collapse, annihilate, and this process contributes to the propagation of your gravitational moment, right? If your energy of your particle is much smaller than the mass of these two particles which you need to create, the probability to create this particle should decrease. So it means that this contribution of this diagram to the propagation of the gravitational mode is going to be very weak. Okay? This is the whole point. The divergences are the same. The divergences are not affected by the relation between mass and the energy of external particle. The divergences are not physical. You subtract them and you go out with your finite part of the diagram. Okay? So in the finite part, you can observe this, what I said, that this the contribution of these diagram disappears when you have external momenta much smaller than the mass. This is called decoupling theory of Christian Krasov. Questions? By the way, you can interact and ask questions whenever you want. Okay, no problem at all. Actually, I like it. So the typical integral you have to evaluate is this one. So you see we have, this is exactly the same loop, and momentum, external momentum is P, and the integral is over K, okay? So this is I4, and you can calculate this diagram, this expression, in any regularization. You need regularization because, as I explained yesterday, here we have logarithmic divergences. Okay, if you go to very high momentum, then there is K4 in the denominator, K4 in numerator, and they produce logarithmic divergence. So this logarithmic divergence must be regularized and eventually normalized. So the question is to choose regularization. If you go to our book with Bookbinder, you will see that there is a discussion of two different regularizations of cutoff in the Euclidean momentum and dimensional. Here I will deal only with dimensional because it's simpler for this diagram. So we start with the following. We just change four-dimensional integral to the dimension 2 omega. Omega is complex number. The best reference on dimensionalization, of course, is Leibrand. Everybody knows this paper, I guess. Okay, it is from late 70s. So my students, every generation of students, there is somebody who opens all calculations, sometimes extends these calculations, things like that. So it's not that difficult. When I was a student, I was also reading this paper. So then we know that in dimensional regularization, logarithmic divergences manifest themselves as the pole of 1 over 2 minus omega. We will see it in details, okay? So the answer for this e to omega is the divergence multiplied by some local expression. This locality of this expression can be proved in general form. It's called Weinberg's theorem. Weinberg's theorem states that contour terms, which are necessary to remove ultraviolet divergences, are always local. Plus some finite term. And of course, our interest is, first of all, to establish this finite term and first find its relation to the pole term. And finally, there is something proportional to 2 minus omega in first and higher powers. It means that this expression vanishes when we go back to omega equal to. Questions? I guess many of you are familiar with this, but if not, believe me, there is absolutely nothing impossible to understand. This is something simple, this dimensional regularization and these calculations. The only difficult part, I would say, is the so-called analytic continuation. This you need to be familiar with the calculus of complex functions. Then there is a theorem of analytic continuation. And this analytic continuation is exactly how to go from this to this integral. After that, the rest is quite simple. So, how we deal with this integral? First of all, we introduce the so-called Feynman parameters. In this case, it's sufficient 2, alpha 1, alpha 2. And we have this Gaussian integral. Okay, Gaussian integral. So each of these denominators is transformed into exponential of minus alpha 1 k squared plus m squared or alpha 2 k minus p squared plus m squared. Then we change the order of integrations. Since there are transparencies, I didn't know that I will have 1 hour and a half. So I have this very condensed form. So first you write this as the integral over alphas, and then we change the order of integrations. And you see that we can actually take this is a Gaussian integral, and we can take this integral. This is, as I tell my students, this is the unique integral we know how to take. It's Gaussian integral. So after we take it, we arrive to this expression, okay, which is very nice. Now we took integral over momenta, and we only need to take integral over alpha 1 and alpha 2. And this integral can be, by some change of variables, can be reduced to the gamma function, okay, to the gamma functions. And this shows that these three expressions, which you get, always produce pole of 1 over 2 minus omega, okay? Gamma functions, I guess everybody know. The last ingredient, mathematical ingredient, which we need, is the volume of the m-dimensional sphere, Okay, because here you see we need m-dimensional sphere. Then this is the answer. This is the answer. You can, as an exercise, calculate this. You can calculate it in two ways. First, you can just introduce spherical coordinates in m dimensions and take the integral. It is very bad way because it takes a lot of time. Okay, once I had nothing to do, I took a piece of paper and started to do it. 30 minutes after, I understood that I don't like to go to finish because I can do it. Probably it will take like 3 hours. So it makes no sense. But there is a trick, okay? And you can find in our book with Bookbinder. I took it from some book on statistical mechanics actually. You can do it in half a page to get this volume of the n-dimensional sphere. And after this, everything gets simple. It does not go. Everything is simple. And you end up with this expression. Okay? With this expression. So you have only one integral over alpha, other integrals disappear. And so you have pole term, and gamma is this Euler-Mascheroni constant. And then you have integral over alpha. Equivalent integral you can find basically in any book on electrodynamics. So there is nothing new in all this what I'm telling you. So after that, we just, how we take this integral? You see, this is a non-trivial integral because here is omega minus 2, and omega is going to 0, to the limit. We intend to take a limit, omega to 0. So we make it in the following way. We replace this expression, we take out m squared in the power of omega minus 2 to make the variables dimensionless, like this tau. And then we exponentiate. So we write, we take exponential of omega minus 2 multiplied by logarithm. Then we take this exponential and we know that omega is going to approach 2. So it is a small quantity. Then we can expand it into the power series up to first order. Higher than first orders are not important because they will produce a vanishing result. So basically this expression transforms into this expression. Okay? It's not difficult. After that, we still have this integral over alpha. So we have here divergence. Okay? Everything is done. And we have this integral. This integral depends on tau. Tau is exactly what we need. Tau is k squared over m squared. Okay, where k squared is the Euclidean momentum and m squared is mass squared. So basically we need two limits. Tau goes to infinity and tau goes to 0. Ultraviolet and infrared. Then this integral, most of the books don't take this integral. They just work in the integral representation. But it's actually useful to take the integral. We take it. This integral is not easy to take. It looks like an exercise from Demidovich or some other book on mathematical analysis. It is possible to take, but you need to make some smart steps, some change of variables. Otherwise, it becomes immediately becomes very big calculation. But if you make some change of variables, then you can find again in the book. Then it's not difficult. So finally, we arrive at this red answer. This means that we have here logarithm of this expression, 2 plus a, 2 minus a. A is this expression, okay? It's 4k squared over k squared plus 4m squared. If we go to the coordinate representation, then k squared replaced by minus box, and we have this. Box is Euclidean, okay? So it's actually a 4-dimensional Laplace operator here. So we can see that in the ultraviolet, when k squared is much greater than m squared, a squared goes to 4. So we assume that a is equal to 2 in the ultraviolet. In the opposite limit, when mass dominates, then a squared goes to 0 and a goes to 0. So our interest is to trace what happens between 0 in the infrared and 2 in the ultraviolet. Question? I can take children. This day I can do, I think I know my part. Let's do it. This is calculation. Good. So we came here, right? Next. So by the end of the day, we have this expression. Okay, we have this expression, we have this divergence, then we have gamma, which is Euler-Mascheroni constant. We have this guy. This is a non-trivial point. By the way, maybe it's worth to come back and explain. Because, you see, we have here m squared in the power of omega minus 2. We want to make the same trick with this quantity. We want to exponentiate it and so on. But to exponentiate it, we need to make it dimensionless. So how we do it? We introduce mu, which is an artificial parameter, which is called parameter of renormalization. Omega is called parameter of regularization. Okay? We just parameterize our divergence with regularization. Mu is a parameter of renormalization because all this minimal subtraction scheme is based on the following trick. You work with mu and then you interpret mu. But originally, pay attention, that originally there is no mu. Mu does not exist here. Okay? So mu is something you introduce to the theory. So by the end of the day, mu disappears because it was not there from the very beginning. So there are no mysteries. So mu does not exist. Still, mu is very useful. You introduce it, you use it, and then it disappears. Okay? Some people tried many years ago, like 15 years ago, some people tried to make some physics out of the disappearance of mu. It's impossible, believe me. So mu, it disappears by definition. So it does not depend on any physics. It's mathematical thing. So what we do here, I skipped this part, is just, maybe I can write it. So we do the following. We take m squared omega minus 2, we write it as mu squared omega minus 2 multiplied by m squared over mu squared omega minus 2. And then we say that this is mu n minus 4 because n is 2 omega, okay, the dimension. And then we have exponential of omega minus 2 log m squared over mu squared. Okay? And then we expand this into series and we get mu n minus 4 multiplied by 1 plus omega minus 2 log m squared over mu squared. Okay? If you take any introduction to renormalization group, then all the in minimal subtraction scheme. All the work is about this. But in fact, mu is also here, and these two mu's of course cancel. But before they cancel, you can make out a lot of use of this. Okay. So after that, you see, by the way, that here we have m squared over mu squared in this string, and we write this expression. So you have here divergence, gamma, which is nothing, and log, okay, and mu in n minus 4 is here. Very good. So what we can observe here is the following. First of all, we see that there is a divergence. Divergence is nice, okay, because it's simple, we can subtract it. Then you have log, and the coefficient between the in front of divergence and coefficient of this log are equal. This is a general rule. Okay, I don't have any exception from this rule. Recently, some people published, I know them very well, very well-known people. They published papers saying that there is a discrepancy between mu and this part. But well, I'm not sure that this is correct. And finally, this is y. Y is what we need, is the final part. Okay, let me remember once again what is y. So y is, y is this log part. Okay, so log part is exactly the final part of the diagram where all the physics lives here. So we have to find the limits of this physics in the ultraviolet and in the infrared. So this is this non-local form factor. Non-local form factor is going to tell us everything about ultraviolet limit and about the decoupling in the infrared. I'm repeating things intentionally. I wanted to ask some questions, okay? Because I came here, go every day by metro and so on, just to make you ask questions. So if you have questions, we'll be very good. Okay. So one interesting detail is the following. If we make calculations in any other regularization, then the coefficient of the divergence will be the same. It was stated by Salam in 51, and we consulted some people who was longer than us in this business, and they told us that after this nobody ever proved this, and nobody ever contested this. What it means? It means that if we go to this divergent expression, the coefficient of this 1/2 minus omega will be the same. You can use Pauli-Wheelers, you can use cutoff, you can use cutoff with three-dimensional integral, you can use cutoff in the heat kernel expansion, you can use Pauli-Wheelers with higher derivatives, you can use adiabatic regularization, and whatever you want. The coefficient of the leading divergences will not change. Okay? And of course, this form factor will not change because it's finite. So it means that what I'm telling you is not just linked to dimensional regularization, it's quite general. Okay? And curiously, nobody ever proved this after Salam. So in particular, the correspondence rule between cutoff regularization and this dimensional regularization is this. Okay, you can find this in the book, some proof of this for two diagrams, but not general proofs. Very good. So, if we think about realization group, then we need to compare the dependence of mu square and or k square. Okay, and this would mean equivalence between minimal subtraction scheme, which is based on mu, and the momentum subtraction scheme based on k square. Once again, why minimal subtraction scheme is so simple? Because minimal subtraction scheme works directly with log of mu, and log of mu always goes together with divergence. Divergence is something easy to calculate. So in minimal subtraction scheme, you just calculate divergence and you get what you want. Okay? Like in scalar field theory, lambda phi 4, if you ask me to calculate divergence of this theory, it will take me at most 2 minutes, because I have formula in my head. Okay, the general heat kernel result. I will just apply, it's 2 minutes, and I will give you divergence. Okay, but if you want to calculate form factor in this theory, you have to work. Okay, so divergences are simple. So let us go to ultraviolet ratio. In the ultraviolet, you see that this a square becomes this expression. So as I said before, it is 4 plus some correction. K is much greater than m. Then our integral boils down to this expression. So we see that here, instead of log of mu over m, you get log of mu over k. And log of m cancels in this limit. So in ultraviolet, there is a perfect correspondence between log mu and divergences. This is the secret why minimal subtraction scheme works so well. Okay? Now, yeah, here I have nothing to say more. So the secret is that if you take books like from 60s, like Berestetsky, Spitaevsky, or Schweber perhaps, or something, what people do? People look for the log of k. Mu was not invented at that time. Mu was, I said, invented in 70s. So after that, things became extremely simple, because you don't need to make real calculations, you just calculate divergences, and divergences is for everybody to calculate easily. Okay? Now, infrared. Infrared is much more tricky. So let's take infrared limit, take this y, put it to Mathematica or do it by hand, it's no big difference, and you arrive to this expression. So you see that here, first of all, no logarithm disappeared. And second, we can see that here we have quadratic decoupling. So as far as k square goes to 0, this y, the form factor, the physics, disappears, and it disappears quadratically. This is equivalent to Zapek-Witten correspondence theory. This is a general rule. If you have massive field and very small Euclidean momenta coming to the loop, then the contribution of this loop dies quadratically. Which contribution? Finite contribution. Divergences? No. But divergences are not physical, we subtract them. Once again, okay? So, physical, in this case, what's very important? There is absolutely no connection between divergence and this form factor. The connection is lost because the log part, logarithmic part, which was like friend of divergence, it died. We don't have it anymore. So what we have is quadratic decoupling. Okay? So divergence does not inform us about what's going on here. Question? No. Okay. So we can make the same with the beta function. So we make the subtraction and t squared equal to m squared, or you can go to m squared. People in many cases do, but the formulas are the same. And take this limit. This is called beta function. Okay, you can do it with p or with m. If you do this in QED, you have your general physical beta function. Okay, beta function. It shows you how you have a running of your electric charge. In the next transparency, I will explain in details what it means. In the ultraviolet, you have this answer. This is any textbook on electrodynamics has this formula. So this is normal beta function for QED. It is positive because of the zero charge problem and so on. Now, in the infrared limit, you have quadratic decoupling. This is the Napier-Carasone theorem, literally. Okay, so you have quadratic decoupling in the infrared, no connection to divergences, and in the ultraviolet you have like very direct connection to the divergences, and things are very simple. Very good. Now, let me here. I will say something which is not about this talk. In principle, everything looks simple, but in some cases, we can calculate divergences, but we cannot calculate the final part of effective fraction. Okay, this form factor, or we can calculate, but we don't know how to use it. In this case, we have to switch on our imagination and try to imagine what happens with this finite part which we cannot calculate. And as usual in these situations, people have different opinions about this. This is what means the difference between beta function and in minimum subtraction scheme and momentum subtraction scheme. You see, this is inverse square of the electric charge in QED, and this is t. T is log of mu. Okay, t is log of mu over mu zero. Mu zero is some value which you take as a reference. You see, the dashed line concerns this minimal subtraction scheme. So you see, in the ultraviolet, in the infrared, it's a linear function. So it is inverse logarithmic dependence, but in the with t, so when you use variable t instead of log of mu over mu zero and inverse charge, the square of charge, then you have linear behavior. But the physical beta function, the dependence of momenta, is not like that. In the ultraviolet, it is parallel straight line. So in the ultraviolet, if you know one, you know another. The difference is a small shift of the basic level. In the infrared, no. In the infrared, this physical beta function goes to zero, and E squared does not run. E squared does not run. Okay? Now, what means this running coupling? What do you mean by running coupling? Let me show you one more thing. This is QED. So, in principle, if you take this calculate in the ultraviolet, in the far ultraviolet, mass of the electron doesn't matter. So you can write the action of electromagnetic field, which other lecturers show you in several versions. Okay, but I put here E squared. What it means? It means usually we put charge to the fermionic part in QED, right? But we can absorb charge into electromagnetic field. If you want, I can explain. Okay? And then your charge will appear here in front of the electromagnetic action. Then we add the quantum contribution. In the ultraviolet, it's just beta. I put tilde because it's not conventional beta, there is some coefficient, and positive. and log. Very good. So what it means? It means that imagine what I will do with this quantum correction. This is my quantum correction. It has log of box. I wanna see how it affects the behavior of the photon. It's impossible, simply impossible, because first of all, log, even if it would be log of 1 plus box, you will have infinite expansion in the series, power series in box, right? So if you try to put, let's say, boundary conditions, how you put boundary conditions to the operator of the infinite order? We don't know, right? This is some very strong non-locality. But here it is worse because log of box has no expansion in the power series. So mathematically the problem is hopeless. But we don't need to do it. Why? Because log is known to be a slowly varying function in the interval. So if you go to atomic physics laboratory, okay, in Juiz de Fora, it's on the first floor, so I always tell students go there. So it measures the charge of the electron. We know that alpha e squared over 4 pi will be 1 over 137, right? But if you go to the accelerator of electrons, okay, there are many of them, like one in Campinas, for example, then you will measure in the energies of like 100 MeV. And you will have different value. Why? Because this log, okay, will increase the magnitude of effective charge. So you don't need to deal with this log as with the function of box. You just say that box over mu square is some coefficient, such that log contributes to the with beta function, change this factor, it becomes bigger than 1 or smaller than 1. And then you have your e squared different. So in the accelerator you have like 1 over 128. In atomic physics laboratory 1 over 137. This is because you are physicists, you are not mathematician. You not always need to worry about boundary conditions, things like that. You just say, okay, it's a number for me. This log for me is a number. Because in this laboratory, this log has fixed value. It doesn't change too much. Okay, if one electron has 20 times more energy than another electron, the log does not change. Okay, the log is essentially the same. So why should I worry about boundary conditions in this case? Okay, this is the idea of randomization group. This is the running company. In reality, if we calculate this form factor, it's much more complicated. So you have this this expression, so it's not log at all. Then you have this guy. It boils down to log in the ultraviolet, of course, yes. But there are some other tricks you can see in this paper, like multiplicative anomaly and whatever. Some ambiguous.
Sorry, I am a little confused. Who is the Feynman diagrams of this? Are the loops you show?
Sure. Good question. So, this polarization operator diagram. Here is A mu, A alpha, and electron loop. Okay? Now, what's interesting is that you know that in QED at one loop there are two other diagrams. For example, this one, okay, and the vertex. And this one is much more complicated actually because here you don't have the loop of massive field. Here you have mixed loop of photon and mass. And the behavior of this diagram, okay, it also has this quadratic decoupling, but in a different way. I will show you for some example with higher degree. Okay? Yes. Okay. And and here it's actually more subtle because the external line is cannot have zero energy because here is a mass of electron. Okay, but in gravity, in many cases, we need a situation when external leg is light. We change a lot the game. Okay. Good. So let's go to gravity. The question is, how we can apply this understanding of decoupling and things like that in gravity? In gravity, we know as we discussed yesterday, that in principle, if you have more derivative gravity, for example, then you have massive ghost. And you may have, if you have more derivative, you may have, instead of ghost, you may have tachyonic ghost. Actually, even here, if you make a mistake with the sign, put here, instead of negative, put it positive, then you have tachyonic ghost, which is another animal, much worse than a normal ghost, okay, which gives you instability in any interface. Then you have R square, which produces a normal particle typically, okay? But also, if you make a change with sign, it gives you tachyon. How we can formulate here the question of decoupling and which kind of decoupling we can have? First of all, we have to use this parameterization of the metric, which we discussed yesterday. So it is G menu equals to eta mini plus H mu. Okay, this is flat and metric perturbation. And look to the, if we want some information, contribution to these terms, then we have to analyze the bilinear form of this section. And this bilinear form of this section has this tensor structure. So you see, this is H mu, this is delta mu alpha beta. This is a unitary matrix in the space of the metric. I need to write it. So, this is called David. Rice David operator. Okay, it's unitary matrix in the space of symmetric tensors. Okay, Rice David was the man who created this science paper for almost. So you have here this delta, then you have this. Okay, you can use these two operators to produce, for example, the projector to the traceless state, but we can do it in different ways, so let's skip this part. Then there is this operator which is related to the projector to the vector state, and these two guys are also important, okay, because they complete the set of projectors. So it's interesting that you may have any theory, like I showed you yesterday, the theory with non-localities, okay? And you still have absolutely the same tensor structures. What changes is these functions, are these functions A1, A2, A3, 4, and 5. So what we will discuss first is that we take a loop of matter fields with external lines of H mu, H alpha beta, and this was done by Gorber and me, and then Kadelius and Nusu did equivalent calculation. I think they used more heat kernel. So, and you get your functions, A1, A2, A3, A4. It's completely non-trivial task because when you calculate, you get something in the tensor expression, which is very big. It has divergences and it has finite part. And you have to separate it and attribute to different to these four terms. Note that we did not include here Gauss-Bonnet and box R because they are surface terms, they don't contribute to the propagation. So, if we do this, this is possible. Why? Because each of these four terms has its own combination of these five functions. So if you give me these formulas, A1, A2, A3, A4, A5, I can separate it in a unique way into these terms. Okay? There is no ambiguity. And this can be done. I think it was done by Gorber and me, maybe it was unique calculation of this kind. And the result is the following. Here we have divergences, epsilon mu. Epsilon mu is, as usual, divergence. plus log of 4 pi m mu square over m square. This is a universal combination, as I explained. And then we have divergences in the cosmological constant term, divergences in the Einstein term, R. Then we have here, again, divergence. But in the last two cases, there are also form factors with the same y. Remember that y has logarithm. Okay, this is the y. And the KR. This xi tilde means psi minus 1 over 6. It is for scalar field, the non-minimal parameter. So it's completely non-trivial point that the first two guys don't have form factors. Why? Why is like that? Because these form factors, y and so on, they depend on the box. What will happen if box acts to lambda? Lambda is a constant. You get 0. So we cannot expect here this non-trivial form factor in the cosmological constant. This is exactly what I said. We cannot make calculations and we use our imagination. In our case, actually it's possible to calculate the form factor, but this form factor is a power series of surface terms. So it's completely unclear how to use it. Okay? It's not clear how to use it. We are thinking about this. So, yeah.
I have a question.
Yeah, sure.
Can we think of the H mu in a certain way, like a gravitational wave or something like that?
Yes, you can. Yeah, you can, but not normal gravitational wave is not the h mu. It is traceless and transverse part of gravitational wave. But yeah, it is a contribution to the gravitational wave. Exactly. Yes. Also, but let's say for physics of gravitational waves, unfortunately, all this is irrelevant. Okay, when I was editing this handbook of quantum gravity, I know personally some most important people in the physics of gravitational wave, and they are friends of mine. And I asked them to write reviews for this, and they said no, because it's poorly classified. What we want to say in this review is that there is nothing quantum. So you have merger of these two black holes, and there is nothing quantum. It's all classical, according to them. Okay. Recently, I had very hard discussions with one cosmologist about it. So, but he thinks that there is something, but I trust the majority of other people. So, this is another approach. If you don't like to calculate diagrams and then separate these form factors into 5 terms, which is a hard work, believe me, you just take this solution, which Ivanov Ramidi got in 89 and Barvinsky-Lutowiski also got in 90. Unfortunately, there is not a single paper which shows how they did it. It's bad. I told this to them. If you follow their paper, you cannot do it. Okay, so this is like a secret knowledge. So, but anyway, the result is correct because it passed many tests, like comparison with these diagrams and so on. So yeah, so you have this expression. This is the solution for the heat kernel. So gamma effective action, you directly take this integral, take your trace in the coincidence limits, and you get it. Okay, for this operator. So it's not difficult. But pay attention, but this works only for this operator. So you need a box plus something, okay? So it does not work if you have 2 different masses, for example. You need only 1 mass, because you have only 1 place to put your mass. This is a critical point. So if you want to calculate something in the theory with 2 masses, like 0 and non-zero, then you have to go to diagrams, unfortunately. Barvinsky told me that he is thinking about how to extend it, but for a while there is no output of this thinking, let's say. So if you take a scalar field, then you, as I told you, this takes like 15 minutes to calculate with program. I have program which makes it. All my students make their own programs, and it always works. You can do your own program. Okay, all intermediate formulas you can find in this our book with book media, and you calculate absolutely the same form factor. Okay, so it doesn't change things. You can do it. Also, this was done in this paper. There was with Sebastian Francino Viñas, Omar Zanusu, and Tiberio was at that time our student, actually before now he's our professor. And Omar is in Pisa in Italy, and Francino Sebastian is trying to get a job somewhere. So yeah, so we did calculations, including we calculated the form factor for R, for linear term. But we have it, but we don't know how to apply it. Sebastian has some ideas about this, but I cannot discuss it here. So now the question is how all this applies to quantum gravity. Because everything I told you was for matter fields, for scalar fields, for fermions, for vectors, for antisymmetric tensor field. Everything was calculated, always gave this result. But for quantum gravity, you have to do the following thing. First, you take a most general model of quantum gravity with ultraviolet complexion. It can be 4 derivative, 6 derivative, 10 derivative, or infinite derivative, if you want. It's important that this theory is perturbatively renormalizable or supernormalizable. Then you calculate diagrams in the momentum subtractions here, which is non-trivial point. Then you can have to make some simplifications because it's basically not simple, but calculation, but it can be done. Was not done yet. And the question is what we expect. So we calculate something which is the quantum gravity in the infrared. Yes, today in the afternoon, I will show you how we work with universal limit of infrared quantum gravity according to John Donahue. And when we calculate something, we'll have to look for the experimental observations to check our theory. This is very important. This is what the main problem of quantum gravity is, that there are no experiments. So, yeah. For example, you have like this theory, okay, as I told you. So you have any theory here, any function here, any function here, okay, and you can calculate form factors, the quantum contributions to this theory. And by the end of the day, there is a statement of John Donahue, who is the main figure in effective quantum gravity, that doesn't matter which action you have here. If you have higher derivatives, then they come with the masses, and the masses are all of the Planck order of magnitude. And if you go to the infrared, then in the infrared, your form factors are defined by this part, by R. Lambda is very small. This is a very, very strong statement, actually. And we want to check this statement. How? We have to start with some theory, which has at least 4 derivatives, and make calculations with these mixed loops and see what happens with these mixed loops. And it's very difficult to do it with quantum gravity. I'll explain why. So what we did for a while with Wagner was the following. We used the so-called model of Antoniadis-Matola. Antoniadis and Matola made this paper in '92. It's very, very good paper, but they used the action which we introduced year before. And this theory is scalar theory with 4 derivatives. And it resembles a lot quantum gravity with 4 derivatives because it has 4 derivatives. I will show you next transparency the action. It has non-polynomial interaction. It admits effective theory in the infrared. It's something which Ignatius Antoniadis and Emil Matola missed in '92, which was natural because Donahue paper appeared only in '94. So, and then it means that we have a very good toy model for quantum gravity. Still, some details are missed here. So, and we will see later on which details. So, this is the action of the theory. Actually, this action appears as a result of the integration of conformal anomaly. Okay, this is the formulas related to conformal anomaly. So, this is the number of fields, conformal fields you integrate out, and things like that. For us now, it's all irrelevant because we can just say that gamma, lambda, and zeta are constants, which we choose according to our will, and sigma is a unique quantum field. So instead of the theory of H mu with gauge fixing ambiguities and so on, we just take sigma, which is apparently free of this ambiguity. Now, this theory has 4 derivatives. Very good. What is the effective low energy theory according to Donahue? It should be universal. So it is this. It's theory without these 4 derivative terms. You see, these last 2 terms are 4 derivatives. And these are second derivatives and 0 derivatives. So we take this, and this is our inference theory. So this is exactly the analog of Einstein gravity. In fact, this is Einstein gravity, but only scalar mode. You know that here your scalar mode has gamma is positive, has wrong. If gamma is negative, yeah, it has wrong kinetic term, sign of the kinetic term. But it's not critical for us because we only want to see how the contribution of Gauss and things like that disappear in the infrared. Good. So calculating divergences in these theories in both theories is difficult, is not difficult. So this is the result for the fundamental theory, and this is the result for the effective theory. We note two details. First, both divergences are for derivatives. This is for derivatives because the theory is renormalized. Okay? So Antoniadis and Matolokas proved that this theory is renormalizable. Actually, I would say that there is no formal proof. So this is, if somebody is interested, it's an interesting thing to elaborate, to prove that this theory is renormalizable. Now, but I would say this is correct, it's renormalizable theory. Regardless, there is no formal proof for why. Yeah, and this is for derivatives, divergences in a second derivative theory. Why? The reason is that this theory is not renormalized, it is the inferred theory. So what we are going to do, we will ignore these four derivative terms and look only for these two terms and compare with this guy and with this guy, because we want to see that this theory and this theory produce equivalent results in the infrared, not in the ultraviolet, in the infrared. Okay? Did you get it? Good. So, what we have for that? We have two propagators. Propagator of the massless mode. If we take zero small mass, take cosmological constant to zero. Okay? Then you have a light or massless mode and heavy mode with this mass, which is basically Planck. And we have vertices, this and others, with many heavy tails. And which diagrams we have? We have three types of diagrams. We have this diagram, is Master's diagram. We know that it produces logarithm, nothing interesting. This diagram, we know very well that it makes us decoupling, according to Apelkis-Karasony theory, nothing interesting. And this is a mysterious diagram because it is mixed diagram, like in QED. But here, on the external lines, you have massless field. So you can go in external tails to zero energy. And you want to see what happens with this diagram. This is a challenging question. And the calculations are not very easy. Okay, yeah, on top of these diagrams, you have these diagrams, which are like snail diagrams and tadpole diagrams. Those are interesting because these first two diagrams contribute to divergences, but they do not, of course, contribute to the form factors, because this integral does not affect the propagating of the particle, right? So it just contributes to divergences. In case of semi-classical gravity, these two contributions combine and give very good correspondence between lobes. But here we don't know. So this is the expression for the self-energy part. You can classify it. The calculations were big, so Wagner used this, how to say, several softwares. So Mathematica and something else. So here is the expression for the one loop correction to the propagator with self-energy parts. Now, instead of one single y, we have several, because we have a, b, c, d, and these expressions. I will, of course, skip most of the formulas, just show you one example, because there are like 5 expressions like this. This is already, I think, with reduced expression, yeah, with this, some hierarchy was introduced, I don't remember by heart. So now we have to simplify and introduce this hierarchy. We can say that momentum is very high, ultraviolet, more than mass, heavy mass, and much more than zero mass, of course. And this gives us these 3 reduced form factors, okay? You can have series. They became simpler, but still it's not a real joy, let's say. Now the question is what we should expect. We should expect in the ultraviolet that these two theories, effective theory and original theory, fundamental theory have nothing to do with each other. But for fundamental theory, we expect that divergences and logs in the form factors will give perfect correspondence, right? And in the infrared, look, in the infrared, in the fundamental theory, we expect that contributions of massive fields disappear. You live with the contribution of only massless fields. And those contributions, according to Donahue, and it is correct, I will open you the secret, it is correct, according to Donahue, we expect perfect correspondence with the infrared of effective theory, because there is only massless field. But in effective theory, there is no mass, so it means that ultraviolet and infrared are equivalent. So we can say that we expect in the infrared limit the perfect fit between what remains from the fundamental theory and what we have in the ultraviolet, or in other words, divergences for effective theory. Okay? So, yeah, those are more big formulas, just to scare you a little bit. Okay? And yeah, and what we found can be reduced to one single formula, one single diagram. You see, this internal line of massive field collapse and produce the Snell diagram. It means that we have quadratic decoupling for this case. So, and it gives you perfect correspondence between this ultraviolet limit in the effective theory and the infrared limit in the fundamental theory. So I would say that at this level, the main assumption of Donahue of 94 is perfectly well confirmed. And in this paper, I doubted this. I will tell it to you tomorrow. There is another point of divergence between me and John Donahue, but this is still, I would say, open. So, but here we agree. So, I mean, Einstein gravity is going to be universal theory of quantum gravity in the infrared. Okay? So, yeah. So this is the expression for your low energy theory. Okay, you have your this is for infrared theory. This is the formula for this bubble-like diagram. So you see that here we have very good correspondence between divergences and log of momentum, and it gives you also absolutely the same formula as in the infrared for fundamental theory. So we have good situation in the following sense, that in this toy model, we can see that effective approach works. Okay, you have decoupling which does not violate your main hypothesis. Now let me show you something explaining what we can expect in quantum gravity. What will be the difference with quantum gravity? So, how we quantize gravity? You do the following. You start with your Fadeev-Popov prescription. Somebody asked me yesterday about Fadeev-Popov prescription. Yes. So you have your quantum gravity action, can be Einstein gravity or any other, gauge fixing term, and ghost term. Okay? And there is certain ambiguity. First of all, if you have a 4-derivative theory or higher derivative, then you need a non-trivial weight function, weight operator, better say. So it must have some derivatives, maybe infinitely many derivatives. Now on top of that you have this expression. Phi is the quantum metric. So you have ambiguities here, beta 1 and beta 2, beta 3 is the weight factor operator. The result may depend on these functions. On top of that, you can parameterize metric in a different way, in several different ways. And in fact, at one loop, there are 6 different gammas, ambiguities to parameterize metrics. This will elaborate in this paper with Tiberio and Jefferson, Gonzalez. So, it means that we can make some reparameterization. Why I said that at one loop it's maximally possible ambiguity? Because at one loop you need only quadratic terms in quantum fields. Okay, if you go to 2 loops you need much more, at least 4. So you have like 100 parameters per. Very good. So we have to expect that our physics does not depend on betas and gammas. But what about decoupling? So you see that we can, in principle, analyze the difference between divergences in different theories using general theories without making calculations. How it works? Imagine I have alpha I is a set of these betas and gammas. I call it alpha I. And alpha 0 is some particular choice which you like for some reason, like more simple calculations, for example. Then general theorems tell us that the difference between two divergences, only divergences, are proportional to the classical equations of motion. Like if you have generativity, then you have this expression. Okay, this is the Einstein equations with cosmological constant. So this is epsilon mu. But this difference is proportional to epsilon mu, and here is some f mu, some extra factor. On the other hand, we know that in all the theories of our interest, okay, these gammas at one loop are 4 derivatives. In Einstein gravity, it's 4 derivatives because it's not normalizable. In 4 derivative theory, it's 4 derivatives because it's renormalizable. In super normalizable gravities, once again, it's 4, right? So in all cases, in all interesting cases, this expression has 4 derivatives, and according to Weinberg's theory, it is local. So you have the local function of this difference proportional to this expression and some f mu. What it means? It means that we can find the general form of f mu. So we know that this is the most general form of one loop divergences. Okay, this is your equation of motion. So the most general f mu is like this. So it has a Ricci tensor, Ricci scalar multiplied by metric, cosmological constant, and 2 differential operators. If we apply this to our case, we get this difference for Einstein gravity. Okay, with epsilon is like this. For Einstein gravity, we have this. And now we can do the following. If we apply this, we can see, if we combine these formulas, you can see the following. Here coefficients are C1, C2, C3, C4, C5, C6. This is what you calculate using, let's say, alpha 0, right? And now you see what you can expect in case of alpha I for arbitrary parameterization, arbitrary gauge fixing. You may have this expression, the product, right? Replace it here and see how you change your coefficient C. The change is like this. So C1 goes to this, C2 goes to this, C4 goes to this, and so on. The unique term which does not change is C1. C1 is the coefficient of the Riemann square. Okay, Riemann square. Now, you have a choice. You can attribute this coefficient to Gauss-Bonnet term or to square of the Weyl tensor. Some people write that this can be attributed to the Weyl tensor. This is a mystery. This is a completely misleading attribution. Why? Because let's think a little bit. In fact, we know that this R mu square, okay, this Ricci square, is a subject of ambiguity, right? Ricci square affects the gravitational wave. Somebody asked about gravitational waves. So Ricci square affects the gravitational waves, and Weyl square is responsible for the gravitational waves in another basis, right? So if you say that this universal parameter C1 is the one of the Weyl square, you're in trouble because okay, this is the Weyl, but this also changes the Weyl term, okay? So you change something, but the only part which is stable is the part which does not affect the gravitational wave. So the correct attribution is to the Gauss-Bonnet, to the topological term. Okay? So we see that in these modifications, because of the choice of different parameterizations and different gauge fixings, you have Gauss-Bonnet invariant unstable. Is it all? No. You may have also this combination, okay, in Einstein gravity. You may have also this combination, which is universal, Okay? So what it means for us? it means that when you make calculations in quantum gravity, in Einstein case, there will be absolutely nothing stable because Gauss-Bonnet you don't observe with these diagrams. Okay, and this combination depends on the lambda, and lambda you basically don't have because you want to plane diagrams, flat diagrams. You are not going to have diagrams on the zeta because nobody knows how to do it. Okay, so it means that in Einstein gravity, quantum gravity, which is our infrared theory, you basically will have nothing stable. Okay, you will have nothing to compare in the infrared. So if you go from this toy model to Einstein gravity, or in other words, if you want, you can choose your parameterization and gauge fixing such that you have whatever you want in the infrared, which is also the same, but from the positive point of view, let's say. Okay? Now, how it is for the four derivative theory? For the four derivative theory, you have absolutely the same combination. By the way, this Einstein ambiguity I will come back to in the lecture of the afternoon and see and show you how you can use it in a different way. So, in the four derivative case, you have exactly the same divergences. You have exactly the same formula for the dependence on alphas, but this time your epsilon is four derivative. What it means? It means that f mu has zero derivatives of the metric. But if f mu has zero derivatives of the metric, then you have exactly this formula. So f mu of alpha I will be metric multiplied by some numerical function, C function, of all parameters. Things simplify a lot. So if you replace this back to your action, you have this formula. What it means? It means that the difference between two effective actions, divergences, is proportional to the conformal shift of the action. Because this is conformal operator. Right? So, if we start with conformal quantum gravity, this is zero. Okay? If we start with R squared term, which is non-conformal, then this guy gives you box R. So box R is going to be subject of ambiguity. So here we can have ambiguity only in the non-conformal terms. R squared, R, and lambda. Okay? Others are completely ambiguous. So this is completely well defined. They are unambiguous. So this is the difference. So the difference between divergences in four derivative gravity is proportional to this. This logic was developed by Fratkinen and Seytlin in '82. I will give reference later on, and then we explain because it's the best paper on quantum gravity ever, for me at least. But it is written such that you need years to understand. So we explained this 12 years after in my paper with student, and I think it's probably my best paper. So of '94. So yeah, how it works. So, but it was developed by Fratkinen and Seytlin. So what it means? It means that if we go from ultraviolet to infrared in the four derivative quantum gravity, we're going to have trouble. So, for instance, this is paper which I mentioned, Fratkinen Seytlin '82. What I say is the best paper of quantum gravity in the history for me. Okay, so they made the following. They found that for Einstein gravity, you have this on-shell well-defined beta function. So you have, for this dimensionless quantity, you have well-defined beta function. There is a way out, actually, if you want equations separately for lambda and g. You need to use this so-called Minkowski-DeWitt effective function, which is constructed to be gauge fixing and parameterization independent. There is this scheme with cosmological constant. There are calculations by Taylor and Veneziano, and we, with Breno Ghiccini and Tiberio, we try to make some physics out of it. You can read it and decide whether you like it or not. So, but it's different story. So, those are the beta functions and equations in four derivative quantum gravity. They're well defined for minimal subtractions here. Okay, this Avramidi and Barvinsky in '85. I think it is a mistake. It should be '86. I will check. So they found these equations they corrected Franklin-Setlin because in Franklin-Setlin paper it was plus 1/36, the fixed point change rule for the second parameter. But okay, so you see, imagine that you will start with this theory, this ultraviolet, okay, and you go to the infrared and wanna see how it will be looking in the infrared. So what we have to do? So first of all, this we can see that ambiguities, the gauge fixing and parameterization dependence in quantum generativity and in force derivative quantum gravity are very much different. So how we can see the decoupling? Actually, to see the decoupling, you need to do the following. First of all, you make calculations and let's say, we want to check, as I wrote here. You want to check that there is the Einstein theory quantum gravity is the universal infrared quantum gravity. Very good. But how? You go from in the fundamental theory. First of all, you have to check that your minimal subtraction beta functions and momentum subtraction beta functions are the same. Recently, Donahue, Percacci, Gabriel Menezes, and somebody whom I don't know personally, claimed that there is a difference. More or less it is clear how they got it. But I would not agree easily that this is correct. So we have like some doubts. But even if this is correct, if the log of mu and log of k gives the same as ultraviolet, what will happen when you go to the low energies? What will happen when we go to the low energies? You have something, you want something to compare. But in the low energies, you have Einstein gravity, quantum, and everything what you can compare is ambiguous. So it means that in the ultraviolet, so masses are irrelevant, and you have you need perfectivity about minimal subtraction and subtraction. That is basically the idea of this Percacci, Donahue, and Gabriel Menezes paper is the following: that ultraviolet limit can be defined in two ways. It can be either case of small mass or the case of high momentum. And they said that when you have two masses in the theory, light mass and heavy mass, then the ultraviolet in one case can be different from the ultraviolet in another case. I am not completely convinced that this works, but maybe it works. Okay, maybe one, maybe another. But then when we go to the infrared, this they didn't do because they used amplitudes, not form factors. You will have Einstein gravity, but in Einstein gravity there is no prediction for this. Everything is ambiguous. So the only thing you can do in this case is the following: is recalculate form factors in Einstein gravity or divergences using arbitrary parameterization or gauge fix, and make the same change of parameterization and gauge fixing in ultraviolet, which is not a real moment because, as I told you, they are different because there is wave function and so on. And try to take care about this ambiguity. The ambiguity must be the same. Does it mean that there is a physical decoupling, the physical equivalence? I don't know. So it is an open question. It's an open and challenging question. So in the last lecture, I will show you how we try to extract physics from all this, and there are also ambiguities. So finally, once again, this is a paper of Franklin-Setlin. Actually, this is in the appendix, third appendix of this paper. There was introduced the idea of effective approach to force derivative quantum gravity in '82, and they show how it works on the Young-Mills example of Young-Mills with higher derivatives. And then in this paper we explained, along with other things, how you catch the dependence on gauge fixing parameters. Okay, so let us make some conclusions. So first of all, the effective approach is our simplest option for quantum gravity. So we say, okay, let us go to only to infrared, because ultraviolet is, by the way, what's interesting to know is that these beta functions, which people worry about, and me too, okay, of course, because I checked these beta functions in some paper and some others. Let us think a little bit. What is the running which these beta functions describe? This is minimal subtraction running. So it is running when the masses, all masses, are irrelevant. One of the masses here is Planck mass. So these formulas describe the running in far above the Planck scale, in the ultraviolet compared to Planck. Do we need this? From physical side, certainly not. Okay, so this is the question is whether we can calculate something in quantum gravity. And here we try to calculate something which has no physical relevance, because it's far below all possible observations nowadays and in future. So what the question which Donahue posed is completely correct and pertinent. He asked what is the quantum gravity which we can one day detect. Okay, so this is an interesting question. And here we need to be sure that doesn't matter what is ultraviolet complexion of quantum gravity. In the infrared, we deal with something we can establish, and this is the Einstein-Hilbert theory, quantum gravity based on relativity. So yeah, and here we come to the decoupling. And for Appelquist and Carasone model, we could check that everything works, like Donahue predicted. And for this four derivative quantum gravity, we cannot say that. We have to check. We have to make real calculations, and including this ambiguity, and see how it works. Okay, and here I stop. Thank you.